Physics Penguin.
Welcome to Physics Penguin's Guide to Energy from Springs. This video follows on from the previous one on stretching elastically and inelastically. What we want to do today is connect forces with energy. This is very important because the two things are different. Forces are pushes and pulls, while energy is the ability to change things. Often a big force delivers a lot of energy, like if an elephant ran through a wall. But sometimes a big force doesn't take much energy. If you're using a drawing pin on the wall, the force of the point is very high, but it doesn't need a lot of energy because it only changes a tiny part of the wall. So what about squashing and stretching springs? At first sight it seems really easy. More force makes more extension or compression, and that means more energy. It isn't that easy really though. Think about this. Imagine some fierce creature attached to a strong bungee cord. He sees you and starts running after you, but the cord is staked to the ground. To start with, he's hardly stretching the cord, so it doesn't take much force and he can move easily. After a short while, the cord is getting pretty stretched. We know that extension depends on force, so if he wants to keep going, he needs to pull harder. Eventually, one of two things will happen. Either the force he uses will be so big that the cord will snap and he will escape, or he won't be able to be strong enough and will come to a halt, barely able to stay in position. Can you see that the force was changing as the cord stretched? We call the energy needed to do a task the work done. It doesn't sound like energy, but it is. Energy is a bit like money. We have lots of synonyms for it. Money can be cash, cost, wage, fee, salary, debt, savings, depending on what you're talking about and what you're doing with it. Well, energy can be work done when you're talking about the energy needed to change something. Normally, work done equals force times distance moved in the direction of the force, or W equals F times S. Yes, distance is usually S nowadays. Don't blame me, I don't make the rules. If force is changing, then we don't have a steady value for it, so this formula just doesn't work. Flippers. So, what can we do? Well, we do have another formula from last time. F equals K times E. This is okay for springs because that's what we used it for. So we can use it with our new formula to replace the fixed value of F that we just don't have. Look at this. W equals F times S. F is varied, so we can fix that by using a mean or average value for the force. S is the distance. Well, the distance we move the spring is the extension, E. So S can be replaced with E from last time. That means that W, our work, is the average F, force, times E, the extension. And that works fine for us, except we still don't know what the mean force is. Well, if the extension is proportional, then the mean of something will be the average of the smallest value and the biggest value. So that will be that the work is the maximum force, take away the minimum force, all divided by 2, and all of that multiplied by E. So what is the minimum force? Well, it'll take 0 force to stretch the string or the rope or the spring by 0 millimeters. So it will just be 0, which means that, if you think about it, work done is just maximum force divided by 2 times the extension. We already know that force equals K times E, the spring constant and the extension, so we can swap that for maximum force, and that gives us work done equals K times E, all divided by 2. And E times E is just E squared. So our final formula for energy in the spring is the work done equals a half times the spring constant times the extension squared. Okay, well that was tricky, so let's pause for a moment. Imagine a stretched spring for a moment. What is it doing? Well, it should be doing nothing really. This means that the energy is stored in the spring, so it's a potential energy. We only have 3 potential energies at GCSE, so it must be either gravitation, chemical, or elastic. Well, clearly it has to be elastic potential energy. How much elastic potential energy is stored in a wire with a spring constant of 25 newtons per centimetre when it is stretched 2 centimetres? Well, let's have a go and try and work it out. Let's use our formula. The work done, or elastic energy in this case, is a half times the K times E squared. So that's a half times 25, the K, times 2 times 2. Well, 2 times 2 is 4, and 4 times a half is just 2 again. So that leaves us with 2 times 25, which is 50. So the answer's 50. No, wrong. What? Well, an answer without a unit is like a day without snow, as we penguins say. We are measuring energy, so we need joules as the unit. It should be 50 joules, or just write J. At GCSE, sometimes you will drop a mark for missing a unit, so just don't do it. It's better to guess the unit than leave it blank. These energy and spring questions often are some of the harder ones, so have a go at the ones on the worksheet and pause the video now. I'll go over the answers when you're done. Don't forget, the sheet is in the video description. See you in a bit. Welcome back. Let's have a look at the questions from the worksheet now. So the main question is the first one, and we need to start by filling in the table. Each column needs a different formula. We have F equals K times E, Hooke's law, which we can use to give us K, and the work equation from earlier, E equals half KE squared, to give us elastic energy. To get K, use K equals F over E to give you the following. So it's just 1,000 each time. Okay, there's a bit of a pattern there. Now the energy, well, that's half KE squared. We know that K is 1,000 newtons per metre, so half K will be 500 newtons per metre. So just square the extension and multiply by that. So we get this. So that's 20, 80, 180, 320 and 500. Notice that these energy numbers get very big very fast. Doubling the force doesn't double the energy, it quadruples it, multiplies it by 4. You might want to compare that to what we did when we looked at kinetic energy. Part B asks about why you would use 5 different forces to investigate a spring, not just one. Don't just say fair test on its own if you haven't explained what that means. Instead, you should say that more results allow us to spot anomalies, odd results or mistakes that we might otherwise miss. It's also true that most real springs don't stretch quite as identically as our example. Lots of results allow us to give a good average result. So part C asks if the spring follows Hooke's law. Well, it says it does and asks you to prove it. Hooke's law is given in the question, so there are no marks for restating it. But we can see that if you double the force on the spring, it doubles the extension. In fact, the spring constant is exactly the same each time. If the spring's constant is actually constant, you must have a spring that obeys Hooke's law. So question 2. Why wear goggles when using springs? You need to state that the spring could snap, and the recoiling sharp metal could fly off quickly in any direction. If it hits your skin, it could cut you, but that probably wouldn't be too bad. But your eyes are so delicate that even a small piece of wire could cost you the use of an eye. Not a nice thought. Well, thank you again for your hard work. I hope you learned something about forces. If you did, why not subscribe to get notified of the next video in the series? Until next time, This is Physics Penguin saying ta-ta.
Physics Penguin.